Hi everyone. Notes 3.3 are on rates of change, and the first thing that we want to do is define what a rate of change is. And a rate of change is how the dependent variable changes with respect to the independent variable, how y changes with respect to x. So here's an example. So here we have some coordinates. We've got the point 23 and the point 52. So this is like a coordinate, but we put it in a chart. And we want to see how the dependent variable right here is going to change. So I want to know how much it's changing by. So here we can say that this is changing by from 3 to 21. It's going up by 18. So the change here is 18. We say positive 18. And this is called the rise, okay? And then we want to see how it changes with respect to the independent variable. How much is the independent variable changing as the dependent variable is going up by 18, and this is going up by 3, and this is called the run. So here, our rate of change would be equal to how much the dependent variable is changing by, how much the y is changing by, which is 18 in this example, over how much the run is changing by, which is 3 in this example. So then when you divide the two, your rate of change would be equal to 6. Now take a look at this. Let's fill in some of these numbers that are missing. So we have 2 and 5 right here. And then here we have 3 and 21. And we're saying that the rate of change is 6. So it's saying that every time the x changes by 1, the y changes by 6. So let's fill in all the numbers between 2 and 5 going up by 1s. So here we can fill in 3 and 4. And if the y was changing by 6, we would add 6 to the 3. And we would get 9, add 6 to the 9, and we would get 15, and then add 6 to the 15, and it brings us to the 21 that we would want. So here it's showing us that our rate of change is equal to 6. All right, so now we're going to talk about how to determine rates of change numerically, graphically, and algebraically. So I'm going to show you how to do all three of these here. So in our example here, it says this graph shows how distance changes over time during a trip. So the first one we're going to do is actually graphically, even though right here we have the word numerically first. And it says choose 2 points to determine the rate of change of the car during the trip. So I can choose any 2 points that I want, but I want to choose points that I can easily identify. So like, for example, this point right here, I can easily identify it because I can see that it is a 1 for my x value and 75 for my y value. I wouldn't want to choose a point like this point right here because I don't know exactly how much it is. For x, I can see, it's 3 out of 5, so it's 3/5, but for y, I can't tell exactly how much it is. So you want to choose points that fall nicely on the graph as much as possible, where there's an intersection between your lines, okay? So here we could use this point, we could use this point, we could use this point, we could use this point. These are all nice, easy points that we can use, okay? So I'm just going to randomly choose 2 points to use. So I will use this point right here, and I will use this point right here. It does not matter which point you choose to use, as long as they're nice points on the graph, okay? So here we want to see how much the y is changing with respect to the x. So what we do is we draw in how much the rise is and how much the run is. So if you see here, this is the rise, and this right here is the run. And the rise is just how much it went up by, how much y changed by, so up or down. And then the run is just how much x changed by. So this is how much it went left or right. So here I can see that the rise right here, it went from this value right here, which we know is 75, and it went up to this value right here, and we know that's 225, because here it's 225 and here it's 75, right? So to find our rate of change, we would do the rise over the run. And because this rise went from 75 to 225, we can say that the rise is 150 kilometers right here. And we know that because 225 minus 75 is equal to 150. So here we can say that the rise is 150 kilometers. And then here the run, we can say here that the run went from 1 right here all the way to 3. So we can say the run right here is 2 hours. So we'll put 2 hours right here. And we know that it's 2 hours because we just take the 3 and the 1 and we can subtract them. And then all we have to do is just divide. So when I divide 150 by 2, I end up getting 75 kilometers per hour. This was graphically right here. All right, so now this time we're going to do this numerically. So we want to insert the ordered pairs from the graph into a table. So let's go ahead and do this. So right here we have two different variables. We have our time, which is our x variable, and we have our distance, which is our y variable right here. And so we know that at 0, 0, right here, we have the point 0, 0. When the time is 0, the distance is 0. We know that we have the point 1, 75. We also know that we have the point 2, 150. We also have the point 3, 225. I'll put that in a minute. And we also have this point right here is 4, 300. And so if we want to find the rate of change, all we have to do is just do the rise over the run. And the rise is how much the y changes by, and the run is how much the x changes by. So you can choose where you want to start, where you want to end. It's totally up to you. So I'm going to start, this time I'm going to start at 0, 0, and this time I'm going to end at 3, 225. I'm just going to choose a different set so you can see that you'll still get the same answers. So here, your rate of change would be equal to, let's figure this out right here. How much did the y go up by? Well, it went from 0 to 225, so this went up by 225. So my rise is 225 kilometers. And then my run right here is how much the x went up by, or the t in this example. And it went from 0 to 3, so it went up by 3. So we can say that this went up by 3, and the time is being measured in hours. Now, when I divide 225 by 3, I end up getting 75. So we can say that this is 75 kilometers per hour. Just a quick note, again, it does not matter what you choose as your starting point and your ending point as long as you are consistent. So let's just take a look at our chart right here. So like, let's say, for example, I decided instead to make 3, 225 my starting point and 4, 300 my ending point. Again, our rate of change is rise over run. And we know that the rise here from 225 to 300 went up by 75. And we know that the run right here went up by, from 3 to 4, this went up by 1. So here we can say that our rate of change is equal to, the rise was 75, positive 75, and the sign matters, and the run was 1. And when you divide 75 by 1, we get 75. And because this is kilometers, and this right here is hours, we can say it's 75 kilometers per hour. So it doesn't matter what 2 points you choose, you'll still always get the same answer. All right, so rates of change, we can see 3 different kinds of rates of change. We could see a positive rate of change, and that will look like this right here. And it's pretty much just telling us that from left to right, the graph will go up. A negative rate of change will look like this, and this is pretty much telling us from left to right, the graph will go down. And then the last type of rate of change that we will see is a 0 rate of change. And that's going to stay the same. The graph will stay the same from left to right. So looking at an example here, we want to compare vehicle fuel efficiency. So the graph shows the average fuel efficiency for an older SUV and a new smart car. Compare the rate of change for both vehicles. So here, for our SUV, I am going to use this point right here and this point right here. And I'm going to see how much did it go up by, how much did it go over by, how much did it rise by, and how much did it run by. So we're going to draw in our triangle right here. So the rise right here is over here, and then the run is over here. So when we draw in our rise and our run, we always want to draw it in as a triangle with just vertical and horizontal lines, no slanted lines. And that's because the rise is always vertical and the run is always horizontal. Okay, so here we have rise, here we have run. So let's go ahead and find our rate of change for our SUV. It's the rise over the run. Let's figure out how much the rise is. Well, this right here we know is at 90. We can see here it's at 90, okay? And this right here went up to 180. So from 90 to 180, this went up by 90 kilometers. And because it went up, it is a positive 90. So here we'll say plus 90 kilometers. Now let's go ahead and find the run. The run went from 10 to 20. So right here, I'm going to go from 10 to 20. That went up by 10. So this is 10 liters. And how do I know to use the 10 and the 20 for the run? The run is the horizontal distance, and the first number always represents the horizontal distance. Also, we can see here that this is 10. And we can see here that this is 20. Okay, just like here, we could see here for our rise, we could see here that this was 90 and that our height here was 180. Okay, so now let's go ahead and divide it. And when I divide these two values here, I end up getting a rate of change equal to 9 kilometers per, sorry, I forgot to put liters here. It's 9 kilometers per liter. So that is my fuel efficiency for the SUV. Now let's go ahead and do the same thing for our smart car. For the smart car, we're going to use this point right here, this 5120 and this 15360. So I want to find the rise right here and my run over here. So my rise is going to go from 120. I can see here that this is 120. All the way up to 360 right here. So to figure out how much it went up by, I would just do 360 minus 120. So my rise right here would be equal to 240 kilometers. So let's go ahead and write this out. So for our smart car, our rate of change is going to be the rise over the run. And we know that the rise went up by 240 kilometers. And then the run, let's see, the run went from 5. We know that this point right here is at 5. And we know that this point right here is at 15. So 5 minus 15 is equal to 10 liters. So here the run is 10 liters. So when I divide 240 by 10, I get 24. So 24 kilometers per liter. So my rate of change for the SUV is 9 kilometers per liter. My rate of change for my smart car is 24 kilometers per liter, which should make sense right here. I can see that the smart car is for sure going to have a better fuel efficiency because it is a smart car. It's made to have better fuel efficiency. That's the definition of a smart car, right? But I can also tell that my smart car has better fuel efficiency simply because my graph on my smart car is significantly steeper than the graph on the SUV. So just by looking at it, I can tell the smart car has better fuel efficiency, but by actually finding the rate of change, I can see that it has better fuel efficiency by 15 kilometers per liter. And that's it for this video. If you have any questions, let me know, and we will get some more practice with this stuff until we feel comfortable with it, I promise. All right, I will see you soon. Bye.